Uh, yeah, okay, so let's get started. So, welcome everyone to the eighth lecture of our CUDA programming. So, in previous lecture, we saw multiple things related to the memory, right? Like we saw the typical memory hierarchy on the GPU. We saw that there are registers, then there is element cache, and then there is L2 cache, and then there is GPU's global memory, which is also known as DRAM of the GPU. And then we saw what is latency, what is bandwidth, and we saw like GPUs are throughput-oriented architectures, and we saw all those things, right? Then we typically saw some examples related to locality, and first of all, we saw different types of locality like spatial locality and temporal locality, and then at the end we saw a few examples related to locality, and yeah, so that was where we stopped in the last lecture. So for the today's lecture, we'll be going through the most important part of the memory, most important memory aspect, which is memory coalescing. Uh, then we'll be looking into something called as structure of arrays and array of structures in the detail. Uh, and then we'll probably look into a few of the examples related to it. And towards the end of the lecture, if we get some time, then we'll also look how to exploit the shared memory, which I used to keep on telling during the previous lecture. Right? So we'll probably see shared few things related to shared memory also in this lecture. And yeah, probably there we'll stop for today. And yeah, so that's the outline for today's lecture. So with this, let's get started. So yeah, so this was where we left off last time. This was the last slide, right? So if you remember, I told you people that what will be how the localities will affect the execution of this two code snippet, and which one uh, which one will uh, which one will exploit locality better than the another one. So we saw that the second snippet was better uh, because the way we are accessing the array ABC is the row major order in this second snippet. While in this first snippet, A and C are accessed in row major order, while the C is accessed in column major order. And typically, the way the matrices are stored in the memory is using the row major order, and hence, since these three accesses are in row major order, we will get decent performance improvement as compared to this when we compare these two code snippets. Okay, so yeah, and 4.7 and 9.5 are the timings which were seen for second and the first snippet respectively. Well, so let's recap about the last slide that we saw in the previous lecture. Now, okay, this was all about on CPU, right? That these things will occur on CPU. Now, what about GPU? So, what will happen on GPU? So on GPU, if you remember, I told that these two localities, spatial and temporal locality, are still applicable on GPU, but the thing is they are not as effective as they are not as effective as they are on CPU. So we'll be able to get some advantage out of the spatial and temporal locality when we run this type of codes on the GPU. But there is something else on the GPU which needs to be exploited in order to in order to reduce the latency of the memory further, and further from this apart from this spatial and temporal locality. And that other thing is something called as memory coalescing. It's called as memory coalescing. And what is this? Let us try to understand it with this definition. So what is memory coalescing? So if the warp threads access the words meaning 32 bits or 4 bytes. So when warp threads, which is the bunch of 32 threads, accesses a word, which is word meaning 4 bytes or 32 bits. When they accesses the words from the same block of 32 words, then their memory requests are clubbed into one. So instead of making 32 memory accesses to the memory controller and fetching 32 words one at a time from the DRAM of the GPU, all these 32 words are brought together. They are just clubbed into one memory request and they are all brought together. And when this thing happens, it is said that these memory requests are coalesced. And that's a typical definition, I mean, theoretical definition of the memory coalescing. But let us see this thing from one example point of view. So if you remember, I'm keep on giving this example, right? It's our classic example, right? Let's say we want to initialize the array to, I mean, all the elements of the array to all zeros inside the GPU kernel. Then you people know, right? The way we write the kernel code. What we do is we specify, I mean, we launch the kernel and we first of all calculate the ID. And we also pass the array inside that kernel, address of that array, which is allocated on GPU. We pass it with the kernel, and then we calculate the ID, which is unique for each thread. And then what we do is we do that thing, right? ARR of ID equals to 0. Now, if you see that ARR of ID equals to 0 is a coalesced memory access. Why it's coalesced? Because if you see the thread 0, which I mean thread having ID 0, will access the 0th memory location. Thread with ID 1 will access the first memory, first element of the array. Thread with ID 2 will access the second element of that array, and so on till the 31st thread. And assuming that this array is an integer array, each word will again, each word is again of 32 bits, because integer is a 32-bit, right? When it comes to C. So here, all the warp threads are accessing the words from the same block of 32 words. And why it's a same block? Because if you people might, you people know, right, that array is stored contiguously on the DRAM or the RAM. So here the block of 32 words is that ARR of 0 to ARR of 31. So each and every thread is accessing that some word from that same block of 32 words. So the example that I gave, that typical example, is a good example of the coalesced memory access. Yeah. So moving on, if that, let us assume that if this coalescing is not there, then what will happen? If the coalescing is not there, then in our previous example, or the example that I just gave, what will happen is that for accessing each and every element in the array, we need one memory request. So for accessing ARR of 0 to ARR of 32 by 32 warp threads, you will need 32 memory requests, and that will just, that will become a bottleneck soon, right? Because such 32 memory access just for one word. But if we have coalesced memory access, those 32 memory requests are clubbed into one, and we'll just need one memory access. So that's the advantage of coalescing. And without coalescing, we'll need one load store instruction for each memory operation. But with coalescing, just one operation for entire one. So yeah, considerable saving, I would say. And one thread would require 32 memory cycles in worst case, when there is no coalescing. When there is this coalescing is not applied, we need 32 memory cycles. And if that's the case, the throughput will significantly reduce, right? Because for one warp we'll need 32 memory cycles, and that's quite costly. 32 memory cycles are quite costly. If you remember, each memory access takes some 400 to 800 GPU, the GPU cycles, so that's quite costly. And 32 for each warp thread it's had a lot of cycles. So throughput will significantly reduce, and if that's the case, then GPU will only be used for compute heavy kernels. Means if there is a lot of number crunching operation going on, in that case only the GPU will be used. But fortunately, this doesn't this is not the case. As long as we are exploiting this memory coalescing property, properly, we'll be able to even run memory hungry kernels on the GPU, as long as we are as long as we are exploiting this memory coalescing property properly. So any questions on this slide up till now? Otherwise, I'll quickly move to the chat. Okay, any questions up till now on this slide? Okay, I'm assuming that there are no questions, and in that case I'll move forward with the slides. Just in case you have any question, please feel free to ask either in chat or unmuting yourself. Okay, so let us understand how this memory coalescing is being implemented internally. So internally, if you remember this, I mean, this memory coalescing is first of all for the warp threads. So across warp threads, there is nothing, there is no concept of memory coalescing, but it's among the warp threads. Uh, uh, it's among the warp threads where this memory coalescing property or concept is being applied. And how is this implemented internally is that, if you remember, I told that warp threads execute in SIMD fashion. So there is so each instruction will be executed in lockstep fashion. So instruction I1 will be executed, then only all the threads of the warp will move to I2. So if that is the case, then the instruction at any moment that the warp threads are executing can either be a load instruction or store instruction or a ALU instruction, which needs some computation. So if it's a load or store instruction, that is, it's a memory demanding operation, then what will happen is, if it's a memory demanding operation, then what will happen is this memory controller will look into the addresses which are required to be accessed by these warp threads, and if this addresses happens to fall in the same block of 32 words, as it is mentioned here. If this memory addresses falls in the same block of 32 words, then the memory request is combined. This entire 32 block of word will be brought to the L1 cache, and all the threads can access this words from this block of 32 words from that cache, L1 cache, or L1 or L2 cache. Yeah, so that is how it is internally happening inside the GPU hardware up to some extent. And yeah, so the crucial takeaway from this slide is that memory coalescing is being done irrespective of, it's not something which is enabled or disabled by the programmer. It's implicitly done at the hardware level. And it's our responsibility as a programmer to exploit this memory coalescing thing, so that our application can reduce the latency of the memory accesses. I hope that you are getting my point, and I'll just move back to the chat in case there are any questions. There is one question: what if one thread hits a memory index out of bound segmentation? Okay, if any of the thread accesses the memory beyond beyond the limits of that process, then there is segmentation error, and in that case there is no coalescing as well as the segmentation fault, both things. So memory coalescing is only applicable if we are accessing within the bound of all the warp threads are accessing within the bound of that 32 block of that block of 32 words. I hope that's clear. Will the whole memory coalescing fail or diverge? Okay, in that case, whole memory coalescing. In that case, your program itself will fail. So I don't see any point of coalescing there, because program itself is failing. But okay, if your question is like this, that let's say segmentation fault is not happening. Let us assume that GPU thread is accessing some memory location which is beyond that block of block which is of 32 words, which is beyond that. Then in that case, more than one memory request will be required. And since it is valid memory location, accesses will be done, but more than one memory access will be required. But the case where it is accessing some illegal memory location, in that case, it's simply useless to think about the coalescing, because your program itself will fail, right? So I guess that is clear. But if something is unclear, then you can just unmute and ask. Could be that fault is stopped by a try block. Okay, I haven't seen try catch block inside kernel so far. But assuming that this try catch is available and is being used to uh, uh, is being used to, find that there is segmentation fault, then in that case, yeah, REST31 threads can access, for REST31 threads, it will be coalesced memory access. So REST31 threads will be accessing from the same block of 32 words. I hope that's clear. Okay, I guess it's clear. Oh. Yeah, so I'll just quickly go back to the slides. Okay, so I hope there are no further questions from this slide. So I'll just move forward from here. So yeah, so let us try to understand this pictorially. But first of all, let us yeah. So first of all, this memory coalescing thing can be easily achieved for the regular programs. Regular programs where meaning where the access to the memory are not in some irregular fashion. Like we are accessing it in a very uh, what I can say, in a very straight fashion. Like we are let's say we are doing some dense matrix operation, in which let us say we are all the warp threads are working on one particular row of that matrix, and within that row they are accessing the different columns. So one thread will access ARR of 0, 0. The another warp thread will access ARR of 0, 1, and third thread will access ARR of 0, 2, and so on. So such kind of accesses are coalesced, and for many of the dense matrix operation, this coalescing thing can be achieved very perfectly because those falls under the category of regular programs. Okay, so that is one thing, and let us see pictorially how this coalescing works. So let us say you have this block of 8 words. Here it's 8, but actually it's applicable for a block of 32 words, but just for the example it's 8 here, but let us assume that this 32 word block. So thread first thread with ID 0 is accessing the 0th memory location, thread with ID 1 is accessing first memory location, and so on till the last thread. And since they are accessing all the words from the same block of 32 words, the memory accesses are coalesced here, right? Because no thread is accessing, no warp thread. First of all, these are warp threads. No warp threads are accessing any word which is outside this block of 32 words. And hence, this is the example of fully coalesced memory access. So I hope this is clear. This is the example of fully coalesced memory access. Then this is the second example. If you can see in this example, this thread number 1, thread number 4, and the last thread, which is thread number 8, are accessing the memory from same block of 32 words. Assuming that this is the block of 32 words, they are accessing from the same block of 32 words. But other threads, apart from this 1, 4, and 8, they are accessing some words which are not inside, which are not falling in this block of 32 words. So this is the typical pictorial representation of uncoalesced memory access. So, but there is one question here I wanted to ask, like, is this thing the completely uncoalesced memory access, or there is partial coalescing happening here? I want you people to quickly think about it and post your answers in chat. Like, is this pictorial representation of completely uncoalesced memory access or partially uncoalesced memory access? Please think about it and put your answers in the chat, or even you can unmute and see. Partially coalescing, or you can even say that it's partially uncoalescing. Yeah, partially coalescing for 3 words. Yes, in that way it's correct. Partially coalescing for 3 words. Partial. Okay, good that you people are at least getting the crux of it. So like here it's uncoalesced memory access, but partially it's partially uncoalesced, because you can see that thread 1, 4 and 8 are still accessing the word from the same block of 32 words. Rest all are, not accessing from this block of 32 words, but there are some threads which are accessing it. So it's the example of partially uncoalesced memory access or partially coalesced memory access. In either way you can say. Okay, that's good. But let us come to this example. If you see this example, what can you tell about this kind of memory access? Is it completely uncoalesced memory access, or partially uncoalesced memory access, or completely coalesced memory access? Please think about this and please put your answers in the chat. Just wait for a few seconds. Okay, let me go back. Varun is saying complete coalescing. Complete coalescing. Completely coalescing. Okay. Any thoughts by other people? What other people think about it? Apart from these three, Varun, Gokul, and Rishikesh. Okay, I guess there are no other responses. Anyways, let's. Yeah. Shri is telling complete coalescing. Okay. I think people are getting it correctly. So this is again the example of complete coalesced memory access, because let us understand why. Because even the warp threads are accessing the memory irregularly. If you see, they are accessing the memory irregularly, but the point here is that they are accessing the memory. They are accessing the memory from. They are accessing the words from the same block of 32 words. Assuming that this is the block of 32 words, they are accessing the words from the same block of 32 words. So again, yeah, if they are accessing the words from the same block of 32 words, then that fits our definition of coalescing, memory coalescing. And hence, the warp threads are accessing the memory in completely fully coalesced manner. So again, this is the example of full complete memory coalescing, and again this is the example of complete memory coalescing, and this falls under partially coalesced or partially uncoalesced memory accesses. Okay, I hope that this slide is clear and there are no further questions on this slide. So let us move on with the next slide. Okay.
Hello.
Now let us. Yeah,
Hello. Yeah.
Please go ahead.
If that block contains more than 32 words, will it become? Hello.
Yeah, please
If
go
the
ahead.
block contains more than 32 words, but there are contents memory of only 32 words of the block, will it be coalesced?
If there are more than 32 words which are being accessed by thread, then it will be uncoalesced. So let us say that, as I told, that word size is 4 bytes, but in some applications, for some case, like let's say you are declaring, okay, so let us say that you are declaring the array of doubles instead of integers. In that case, double will need 8 bytes, right, instead of 4 bytes. So in that case, each and every thread is accessing the array element which is of 8 bytes and which consists of 2 words. 8 bytes is 2 words, and it will need to access. If you are getting it properly, then it will need to access uh, 232. Two blocks of 2 blocks each of 32 words. If you follow that R vector array example, array of I equals to 0 thing. So I hope that's clear. If it's more than 32, if it's going beyond 32 words, then that will become uncoalesced, as well as it will need more than one memory one memory operation. I hope that's clear. Okay, I don't see any. Okay, anyways, there are any further questions, then please feel free to unmute and ask. But yeah, I'll go along these slides. In Okay, so I hope that till this point we are clear, and let's move on. So let us now see the example code. Example code snippets for each and every case, which is completely coalesced. Second is partially coalesced or partially uncoalesced, either case, and third is completely uncoalesced. Yeah, so let us see the example for each and every case. So for completely coalesced, I have already gave you that example, right? That if ARR of ID equals to 0, like we are passing the array to the GPU, and in that array we want to initialize each and every value and each and every element of that array to 0. And that's the example of completely coalesced memory access. So ARR of ID equals to some right hand side, that we are some operation we are doing. So each and every element will be each and every thread will be accessing the contiguous element of the array. So thread 0 will be accessing this 0th location, and thread 1 will be accessing first location, and so on. So accesses are completely coalesced in this case. And yeah, so that is typical example of completely coalesced memory access. Yeah, but now let's come to the second case where the memory accesses are completely uncoalesced. So I request each and every one of you to try writing the code, at least a small snippet of code in which the memory accesses are completely uncoalesced. Exactly opposite to this, like here completely coalesced, you want to write the code corresponding to the corresponding to the case where memory accesses are completely uncoalesced. I'll wait here for a few seconds to try out for you. Quickly go to chat to see if there is. Yeah, please try out case where memory accesses are completely uncoalesced. Try writing the code snippet corresponding to that, and once at least some of you have tried, we'll look into the code of that completely uncoalesced memory access. Please try out so that you people can at least get some idea out of it, like how to do that. We'll wait here for a few seconds. Let me go back. Okay, if you are using big array of log int, and I'm not really sure about the size of that log int, but assuming that size of the log int, the amount of memory it takes to store a log int inside a C, or yeah, in C, is less than 32, then in that case also the accesses won't be completely uncoalesced, right? Because there will be at least two threads who are, if let us assume that size of log int is 16 bytes. Let us assume that in the worst case, then in that case first thread will be accessing that 16 bytes, second array will be accessing that another 16 byte, which again falls into the same block of 32 bytes. So I don't think that using big array of long in saying ID equals to
But
thread
still,
ID.
the rest of the warp threads would be going beyond 32 bits now, sir.
Yes, rest of the warp threads will be going beyond those block of 32 words, right? But is it completely uncoalesced? When the access is completely uncoalesced, let me clarify this. access is said to be completely uncoalesced when we need one. Okay, let me go back to this. Yeah. So if walk threads require 32 memory cycles or one memory cycle for each thread, if one memory cycle is required for each thread, there will be 32 memory cycles required for the entire work. In that case, this is the worst case, right? Right. So this is the example of the uncoalesced memory access. So you should write your code or snippet that you are designing in such a way that you will need 32 memory accesses for the walk threads. And if you
So
see,
then maybe if we,
yeah, please go ahead.
uh, yeah, so maybe if we, so in this case, what we need to do is just increase the size, or is there like a different to it? So we can
Increase
go
the
like
size of.
unsigned long int and keep going like that,
Okay,
or
yeah, I got your point, but instead of just changing the data type, can you do something else? Let it, let let it be int, right? Who cares if it is long, unsigned long int or int? As long as you are accessing some word which is outside that block of 32 bytes. Can you do something such that you are accessing that okay, so if one walk thread is accessing some word from that 32 sorry, block of that 32 words, another thread in the work should not access the word from that block of 32 words. Is the functionality that we want. One way to go with it is the way you told, like we just keep on changing the data types. But yeah, that is okay, but uh, can it be done in a better way? Like, let us take, just let us go with int. And if you want to go, if you want to access more than, beyond that block, then how can we go? Just wait for few responses. Even if you are unable to do it, then that's fine, but let us try.
sir, maybe we could have like an array that is uh, int array that is having 8 different values in it, and like that we will have 32 different arrays, and we will just address the base address of each array. Would that work, sir?
Yes, yes, that will probably work, but 8 will not work. We'll need 32 because one integer takes 4 bytes, and 4 bytes is one word, and in each block there are 32 words. So we'll need to access in the hops of 32. So first thread, thread with ID 0 should access the some element from 0 to 32. Then the next thread, which is thread 1, should not access anything from 0 to 32. In fact, any other thread apart from 0th thread should not access anything from 0 to 32. I hope that's clear. And all other threads should access in that hops of 32. If that's the case, then we can achieve. We'll see how to do that. I'm just looking for some. Okay, Balloon has this equation. This is equation for computing the ID uniquely, I guess. Okay, this big array of long int, that is not the perfect way.
So, calculating the ID in the way where you're going along the block dimension first, and then rather than going within the block, in sense that you're multiplying it with the grid dimension and adding the block dimension, then after the first thread you will go directly to the next block,
Hmm.
and then again to the next block, and then again to the next block. So, or a better way is if we initialize something with like n comma 1, the kernel where.
I got it. Probably that might work, but yeah, that should work. But I think this will get slightly more complex. But anyways, I think that should work. This one will also work. ID into 32. So you are just hopping 32. You are just hopping by 32, 32 uh, in the steps of 32 actually. So I think this will also work. Array of ID into 32. ID into 32. Okay, I'm not
Sir,
sure
could we
about this.
also like, uh, sir?
Yeah, please go.
So instead of actually using like all the threads from each block, sir, could we like have like a bunch of blocks and just like use one thread ID, sir, from each
Yeah,
block?
one thread ID, but
Would that still be called uncoalesced or?
see, if you're just accessing one thread and performing operation with it, then in that case, in worst case, you'll need one memory operation, right? Because you have just one thread. So
Yes, sir, but different warp, sir. Like that.
yeah, but I mean, I already told you in the start of the lecture, right, that this memory coalescing concept is only applicable within warp. Across the warp, there is nothing like coalescing. So coalesced
Okay,
memory
sir.
access will happen within the warp threads. I hope so. That's clear. Okay, so let us go to the slide. I think probably this last two things might work, but I need to check whether it will work or not. But yeah, so let us go along the slides and see how it can be done. So the one of the way in which this can be done is this. You can see this snippet, right? So here, please observe. First of all, please observe one thing. This chunk size variable. This chunk size is the variable which is under the control of a programmer, and it and he or she can modify the value of this variable to make the coalescing. I mean, to change the amount of coalescing. So if this chunk size is 32, then we'll see that if this chunk size is set to 32, then it will lead to completely uncoalesced memory access. How? Let us understand with step by step. So let us say we have warp threads whose IDs goes from 0 to 31. So yeah, 32 threads, ID is going from 0 to 31. Chunk size is 32, as I stated. For completely uncoalesced memory access, we want to check what will happen. So chunk size is 32. And if that's the case, then for the 0th thread, the thread having ID 0, what will happen? So start will become 0 because 0 into something is 0. And will become 0 plus chunk size, which is 32. So end will become 32. And this loop will go from start to end, excluding end. So this loop will go from 0 to 31. For thread number 1, what will happen? The start will become 32 because 1 into 32 is 32. End will become 32 plus 32, which is 64. And for the first thread, this loop will go from 32 to 63 and so on. So if you see, this is the pattern. 0th thread accesses these array elements. In 0th thread accesses this array element from 0 to 31. First thread accesses this array elements from 32 to 63. Second, the thread having ID 2 will access it from 64 to 95 and so on. So if you see, uh, the first thread is accessing the first 32 elements, and after that no other thread is touching that 32 elements. If you are getting it properly, the thread number 1 is only working on 0 to 32 0 to 31 array elements, and that exactly forms one block of 32 words, and then no other uh, thread from the warp is touching that. And similarly for the thread 1, thread 2, thread 3 and thread 31. So I hope you are getting this. So if that's the case, this if chunk size is set to 32, then in that case you will be getting completely uncoalesced memory access. And I'll ask you another question, counter question to this thing. What will happen if I set chunk size to 2? When I set chunk size to 2, how many memory accesses will be required by warp threads? Uh, how many memory accesses will be required by warp threads for accessing this array? Okay, I think it should be now very clear to people. If chunk size is 2, how many memory accesses will be required by warp threads to access this array is my question. I'll wait here for some
16,
seconds.
sir.
How 16? How is it 16? Okay, anyways, I mean, if you feel that something, when you're proposing some answer, you should give some, I mean, what I can say, you should give some convincing argument related to that answer, so that others can understand why you are proposing that solution. That
Sir, like earlier we did like increments of 32, no sir. So like because we are doing increments of 2, if we do 16, so 16 times 2 would be 32.
I don't think that will happen. Okay, let me see what others are saying. I think others are getting it probably correctly, but don't worry. I mean, even if you are giving wrong answer, that's not an issue. We'll understand. We'll understand step by step. Yeah. So I think Varun is getting it correctly. First 16 thread coalesce together. Next 16. Yeah, that's correct. Yeah. Okay. Anyways, I think you people are getting it. So let's go back to the slide and understand what's happening. So when chunk size is 2, let us understand what is happening. So yeah, let us come to our warp only, like the 32 threads, each having ID from 0 to 31, and chunk size is 2. So what will happen is this ID for the 0 thread will be 0. So 0 into 2 is 0, and is 0 plus 2, which is 2. So first thread will go from 0 to 2, excluding 2, so 0, 1. So this and this memory location, this two memory location will be accessed by 0th thread. Then for the first thread, ID is 1, so 1 into 2 is 2, and 2 plus 2 is 4. So from 2 to 4, excluding 4 because this is less than. So 2 and 3 memory location will be accessed by the thread with ID 1, this 2 and 3 memory locations, and so on. The thread number 3 will access 4 and 5, thread number 4 will access 6 and 7, and so on. This will go on. So if you see, first 16 threads will be accessing the words which are in the so first 16 threads will be accessing the words which are in the same block of 32 words, and from the 17th thread onwards, which is having ID as 16, so threads having ID from 16 to 31, which are rest 16 threads, they'll be accessing uh, the words from the another block, which is not this one, and but their accesses will be from the same block of 32 words. So exactly two memory accesses will be needed, and yeah, so that is what is the answer. So exactly two memory requests will be needed if the chunk size is 2. I hope that's clear. If anything is unclear at this point, then please you can unmute yourself and ask, or just put your question in chat. I'll take that up. This is important because this coalescing aspect is the crucial one.
Excuse me, sir.
Yeah, please go ahead.
Hello.
Yeah.
Sir, instead of this code snippet, if we write ARR ID plus 32, so will it be completely uncoalesced?
ARR of ID plus 32. Where you are telling? Here is at this place.
No, instead of this entire code snippet, just
Okay.
I am taking ARR ID plus 32 in each thread.
ARR of ID plus 32. No, I don't think that will be coalesced. Let us understand why. So if AR,
Uncoalesced.
no, yeah, it won't be uncoalesced. Let us understand why. For the 0th thread, it will be 0 plus 32. Okay. For the first thread, it will be 1 plus 32. And
Yes,
so
sir.
on. For the second thread, it will be 2 plus 32, right? And if you
Yes,
see
yes.
this, again, this accesses are from the same block of 32 words. The word that is starting at this 32. I mean, you can ignore the constants, right? If you see this, if the word starts from 32 location, it's 0, 1, 2, and so on. It's the same thing. I mean, again, the memory accesses are
Yes,
completely
yes, yes.
coalesced.
I got it. Yes,
It's
sir. I
completely
got it.
coalesced.
It will not be the first block, but another block, but
Yeah,
completely memory coalesced.
yeah, completely
Okay, got
coalesced.
it. Yes, sir.
Uh, if any further questions, then
Sir, each block we said like 32 bytes, right, sir? Would that always be like constant for the hardware, or
No, no, that's I actually gave that example, right? That for integer, it's the case that the size of that word. I mean, size. We say that size of that word should be 4 bytes or 32 bits, right? But it's just the case with integer, because integer needs 4 bytes or 32 bits on the hardware to store that int variable. But for case of double, you will need 8 bytes. So in that case, it might happen that you need two memory access, right? Because in that case, first 16 threads will be able to access the words from the same block of 32 words. I hope you are getting, because we are now using double, which takes 8 bytes. And if that's the case, each element in the array needs two words, right? To store itself, to store that element. And if that's the case, the word threads would need two memory access, even though the accesses are like ARR of 0 equals to 0, ARR of 1 equals to 1. Okay, let me go back here. Even if the accesses are like this, but if we are using double instead of it, then it won't be completely coalesced, because of the size of double. So we'll need two accesses there, and it won't happen each and every time that I hope that you are getting that this word size is matching with our data type size. But from hardware size, it is hardware side. It's always fixed that the word is 32 bits or 4 bytes. I hope that is clear. But just in case I missed anything, then uh, go further and unmute yourself and ask further.
Clear.
Yeah, hardware side it's fixed, but data type side it's not fixed. Okay, I think there are no further questions from at least this part. So let us move on. So we saw two examples. Sorry, in fact, three examples we saw. First one was completely coalesced. This one. Second is completely uncoalesced when chunk size is 32. That will be the example for completely uncoalesced. And the third one, which is partially uncoalesced or partially coalesced, when the chunk size is 2, right? When chunk size is 2, we have partially coalesced memory access, because we'll, as we saw that we need two memory accesses. So we saw three examples: complete coalesced, complete uncoalesced, partially coalesced. And this way of accessing the array is also known as threaded way of accessing, because if you see, thread 1 is accessing some elements, then thread 2 is accessing some elements, and that is this stride, right? This stride of 2. And this is the pattern in which the elements are being accessed by the array. So this chunk size determines the stride of that access pattern. Okay, so I hope till this point we are clear. Now, third thing is this random access. So let us understand this random access properly. So whenever we have this form of access where we have this ID which is unique to each and every thread, as we know, then we are using this ID to get value from some array which is known as input, and whatever value we get from that input ID, I mean input of ID, we are using as we are using that value as an index to that array. In that case, it completely depends upon the way the values are stored in input array. Uh, I mean, the access to the array will completely depend upon the way the values are stored in input array. So it might happen that some of the memory accesses are coalesced. I mean, some not coalesced, but some of the memory accesses are falling in the same block of 32 words. But other memory accesses go beyond this block of 32 words. It completely depends upon this input, the way the values are there in this input array. So yeah, this is the example of random access, and this randomness comes from this input array. And you might think that where these things, I mean, where this type of accesses are being done. So typical example of this type of accesses is in the graph algorithms. So let us take the example, one of the example of graph algorithms. Let's say BFS. We are traversing the graph, or let's say triple SP, single source shortest path. In that case, what we do is, like, we want to traverse the graph, or we want to find the shortest distance from the source to the sink vertex in case of triple SP. So what we do is, this is the normal operation that we do in such algorithms, like triple SP. What we do is, we for a vertex we go through all its neighbors, right? In triple SP we do that. We for the vertex we go through all its neighbor, and we want to know the distance of that of our neighbors, or sorry, the neighbors of that vertex. So this thing is very similar to that. If you see, for a vertex which is handled by a particular thread, so thread ID is handling the vertex number ID. So for that particular vertex, which has which has ID as its ID, this ID thread ID, and we want to go through all its neighbors. So this input represents the list of neighbors. So we are going through the neighbors of this vertex ID, and uh, we are uh, we are taking its distance out of it. Like let us assume that this array A is the distance array which stores the distance of each and every vertex. So for a vertex, we are going through all its neighbors and getting its distance. So if you see this type of random computation, random access is highly possible in graph algorithms. Typically, the SSSP example that I give. And even in BFS, it happens, right? For the particular vertex, we go through all its neighbors, and we probably might need some information about that neighbor vertex, which is stored in some array. So yeah, so this random accesses are common in graph algorithms, and if you see, this random access leads to uncoalesced memory access. So that is point that you should note here. Okay, any questions up till this point? Quickly. Okay, someone is saying instead of addition, I guess multiplication can do the job. Like, yes, multiplication can do the job. In fact, someone even suggested that, yeah, this one, ID into 32. I guess this will also work because of this reason, like 0 into 32, then 1 into 32, 2 into 32. So, into 32 will work, but plus 32 will again lead to fully coalesced memory access. I hope that I'm clear. And another thing is, I'm hoping that there are no questions up till this point. So if that's the case, then let's move ahead with slides. Okay, so this was about this coalesced, uncoalesced, and partially coalesced memory accesses. Okay, so I think we understood the things up till this point. Now there is one more question that I wanted to ask. Let us say we have this uncoalesced memory access, right? Here, let's say chunk size was 32, right? We understood that chunk size is when chunk size is 32, we'll have completely uncoalesced memory access. But let us say that we want to access this array in similar manner, in strided manner only, uh, in the strides of 32. Uh, let us assume that we want to maintain that thing. We want to access the array in strided manner, but still we want to get the coalesced memory access. Then my question is, how can we get that coalesced memory access? If we want to still get that coalesced memory access, even the access pattern is strided. Can anyone point out some way in which we can do that? I hope that question is clear. Let me repeat the question. Let us assume that the strided memory access is still, it still holds that we want to access array in strided manner, but still we want the uh, memory access to be coalesced. Then how can we get that? That's my question. I will wait for a few seconds, then we'll move on. Just giving some time for you people to think about. Please think about it and post your answers in chat or unmute yourself and say what you think about it. Let me. Okay. think there are no responses. Okay, anyways, I hope that you people are trying, but let us go ahead with slides. Okay, so reduce the number of axes, reducing the number of axes. But okay, I mean, it is not the solution, right? I mean, each thread need to do some work, and reducing the excess won't be, I think, a proper solution for it. Excess can be done evenly or oddly. I think so. This might be the case, but I request you to clarify more on this, like evenly or oddly. How can you do evenly or oddly? I think this might work, but you need to specify what is evenly, what is oddly, and what actually is the access pattern that you will be using. Okay, anyways, let's go back to the slides. I think we might run out of time, so just quickly going back to the slides. So okay, let us assume that we still want to access the array in this strided manner. So first thread will access the elements from 0 to 31. Second thread will access from 32 to 63, and so on. So strided access pattern we still want, but this will lead to uncoalesced memory accesses, right? As we know. But if we still want to make it coalesce, then what we can do is we can just one thing that we can do is we can just rearrange the values in this array. But the way we should rearrange it is like this. So to make it completely coalesced, what we should do is we should take the first element which will be accessed by the array 0, first element which will be accessed by array 1, first element which will be accessed by array 2, and so on till the 31st array. All the first access of each thread we should take, and then put them together at the start of the array. Then in same manner we should take the second element which will be accessed by the thread number 0, second element which will be accessed by the thread 1, and so on till the thread 31, and place them after the all these first accesses are getting finished. Yeah, there we should place the second the elements which will be accessed by this thread elements threads secondly. So in that way we should rearrange the values. So I hope you are getting it. So entire array values in this array will be getting rearranged, so that after that if you want to access the first element of all these threads, then this access pattern will become like this, because now all the first accesses of all the threads are together, so they'll be accessed like this. Then all second accesses are together, so they'll be accessed in the same manner as first accesses are being done. So one way to go, one way to mitigate this issue is rearranging the values inside this array. I hope you are getting it. So with this, let's move further. Please keep this in mind that I told that we need to rearrange the values, and this rearranging thing that I told, where all the same attributes. So here, if you see the first, let us assume that first access or the first thing that each thread of this each warp threads are accessing represents one attribute. So this is first attribute, this is first attribute, this is first attribute, this is first attribute of a particular thread, and then this again is the second attribute, then this again is the second attribute for that particular thread. So what we are doing is we are grouping a particular attribute together, and such kind of grouping, or such kind of way of storing the data is known as structure of arrays, and we'll look deeper into what is the structure of arrays in today's lecture only. But if we arrange our data in that way, then you can clearly see that the memory accesses that will need, the memory accesses that warp threads will need to have will be completely coalesced. So yeah, so there is definitely a benefit of having structure of array instead of this thing, strided access. So when we use structure of arrays, the accesses will be completely coalesced. But opposed to this, there is some second thing also, which is array of structure. Okay, so first of all, this structure of array is good for GPU because there is complete coalescing happening. But there is again second thing, which is array of structures. So think of array of structures similar to this threaded access. So each thread should access consecutive elements of the chunk. So thread 1 will be accessing 0th and 1th memory location. Thread 2 will be accessing 2 and 3 memory location. So that is something strided access, and it is actually very similar to array of structure. We'll see. So this thing have advantage on CPU because if you see, whenever this one particular thread on CPU will access this, due to caching effect, all the elements which are after this will be brought into cache, and since this element is being accessed, all the elements after it will also be accessed by that thread, which will be which will be actually the case for strided access, right? You can see from here. So this strided access is actually, I mean, which is also known as array of structure. I mean, the way it is stored is similar to array of structure. Has benefit, I mean, it gets performance benefit on CPU rather than GPU because of something called as because of this locality principle, which we studied in the previous lecture. So that's one thing. So arrays of structure or the strided access pattern is better on CPU, but this structure of array, which we'll be seeing, both these things we'll be seeing, is something which is done on GPU, which gives better performance compared to this array of structures. Any questions up to this point? I already gave you that example, right? That array of id equals to 0, initializing all the elements of that array to 0. So, okay. So this itself is the example. I mean, there is no, I haven't written it completely, like computation of id and the kernel's signature and all those things. But this is the typical example for completely coalesced memory access. I hope that it's clear for you, Harish. Okay. Okay, fine. If that's the case, then let's move forward with our discussion of array of structure versus structures of array. Okay. Okay, so let us discuss about this array of structures and structures of array further. So let us say that you have some linked data structure, something called sort of linked list or something like that, and you want to store you want to store the information of the entities inside that linked data structure. And for doing that, what you need to do is first you need to define the how the basic entity of that structure basic entity of that linked data structure will look like, which is defined using something called a structure in C. So so there will be the array of this type of okay, let me put it like this one. There is this structure which has this attributes int a, double b and char c, which is character. So okay, so yeah, so these are the attributes of that particular element of that linked data structure, and we are declaring the array to create that linked data structure, and each element of that linked data structure will be of this type, this node type. And yeah, so let us see, let us put this with an example. So let us say that you want to store the details related to the students. So how can you store that? You can do something like this. So you can declare structure which detail out the information about each student. So first, so here you can store the attribute of student. So first attribute might be int roll number. So it stores the roll number of the student. Then double marks corresponding to the student, and then character, the name corresponding to that student. So all these things you can store. I mean, those are the attribute of the student. And then to store the information related to the multiple students, what you can do is that you can declare the array of such students, and each student, I mean, each element of this array will have this attribute ABC, which is roll number, marks, and name. So we are declaring array of students where each student is having these attributes. So this way of declaring array using this structure is called as array of structures. If you see, we are declaring array where each element of the array is structure. So it's array of structure. Suppose, I mean, okay, let's move on. So good thing about this, good thing about this array of structure is that it gives performance benefit on the CPU, because we already saw in the previous slide, right? The reason for this is already covered in the previous slide, but let us understand it betterly here. So when you have this array of structure, it gives performance on the CPU because of the locality, better locality. I mean, the locality which is being exploited in better manner in this data structure. How? Let us see. So when a thread accesses an attribute of the node, please note that attribute is this roll number or marks or this name of the student. When a thread accesses an attribute of a node, so let us say a thread has accessed these attribute roll number, then it will also access the other attributes of the node. So if that thread has accessed the roll number, then it is likely that that thread will also access its marks and name of that student. And if that's the case, it will give benefits on CPU. Sorry, it will give performance benefit on CPU because of the caching effect. So whenever this roll number is bought, this marks and name corresponding to that student will also be brought into the cache, and hence because of this locality principle, on CPU will get significant performance benefit. On GPU, this caching effect is there, but as I mentioned in previous lecture as well as in this lecture, that caching effects are not as prominent on GPU as those are there on CPUs. So on CPU will get better performance for this type of AoS data structure, which is array of structure data structure, than on GPU. That is one thing. But in order to exploit the performance, I mean, in order to get better performance for such type of, I mean, let's say we want to perform such type of operations on the students attribute, right? So how can we do it on GPU? So on GPU we need to exploit something else, and as we all know that something else is the memory coalescing. So how can we access this kind of thing in coalesced manner? So for that there is something called a structure of arrays, and the way the structure of array is done is like this. So instead of storing each attribute in this manner, like first, so here the storage will be like this. So one element of the array will be having ABC. Then another element of this array will be having its ABC. So if one thread is accessing the roll number of that student, and another thread is also accessing the roll number of the another student, then in that case the access will be strided, right? Because the roll number is here, then between that roll number and I mean the roll number of that student and the next student, there will be this name of the first student and the marks of that student. So this is something sort of a strided access for the GPU. And as we saw that strided access will give some, I mean, performance degradation, because memory coalescing is not being exploited to 100% in that form of access. So in order to make memory accesses completely coalesced on GPU, we use something called as SoA, which is structure of arrays. And how we do it? It is like this. So here we are declaring, please note that here we are declaring the array of size n, where each element is of size node. But here we are just declaring one structure for the all n students. And how the structure of for all n students is designed is like this. We have the roll number corresponding to all students together, the marks corresponding to all students together, and the name corresponding to all students together. Now if you see, if there are two threads, or let's say if there are 32 threads, and they are accessing the roll number of that all 32 students simultaneously, then the accesses will be coalesced, because this it's stored in the array, right? So it will become something like this. If you see, it will be like this, because roll number is an array and it's stored in contiguous memory location, and each thread will be accessing, each thread of the work will be accessing the contiguous memory location, which is the words from the same block of 32 words. So by storing attributes in this manner, we'll be able to exploit the memory coalescing up to 100% by this form of storage, which is structure of arrays. And so advantage of this is when a thread accesses an attribute of a node, let's say that attribute is roll number. So thread 0 is attributing the accessing the roll number attribute of this. If thread 1, thread 0 is accessing the attribute roll number attribute of student 0, then its neighboring thread accessing the same attribute. So thread 1 accessing the again the roll number attribute of the student 1. If that's the case, then the same attribute of the next thread, and in that case the coalescing will be better because both of them are accessing the same block from that same word from the block of 32 words. And yeah, this can achieve up to 100% memory coalescing. I hope that's clear. I think I was a bit unclear here. If there are any questions, then please feel free to ask, or unmute yourself and ask, or type them in chat. Okay. 16, I guess for 16 threads access one index and 16. I don't think that this will work. I hope that you are telling this for that how to get coalesced memory access even having the strided access pattern. I hope that this is the answer for it. I am not able to calculate how can we use this even odd thing to get coalescing. Okay, anyways, if you feel that something I am missing something here, then you can unmute yourself and ask here. Okay, anyways, I'll move on. Sir, will you be able to provide an example? Okay, I think I already took up this question. So yeah, any questions up till this point on this slide? This is a very important concept. If there are any questions, then please feel free to ask. For area of structure and structure of array. Just hold on for a few seconds, 4-5 seconds. I guess there are no questions in that case. Okay, let's move on if there are no questions. I'm assuming that you will have understood what is array of structures, what is structures of array, and why SoA, which is structure of arrays, is able to exploit coalescing better than array of structures. So the key thing or key takeaway is that array of structures will have this strided access pattern, and this stride will be determined by the number of attributes that are there. And in case of structure of array, we are getting fully coalesced memory accesses because all these same attributes are together. So that's takeaway from this array of structures and structures of array. Okay, so I'm hoping that you people have understood this. So assuming that you have understood all the things, I'll give small classwork to write the code for both of this case, and you should be able to use CUDA memcopy to copy the data from CPU to GPU, perform operation on such kind of data structure, and after performing the operation, you should be able to copy the data from CPU to GPU. And yeah, please request you to write the code corresponding to this two cases. And yeah, for the GPU, right? Both of the code for the GPU. So you need to write the kernel. You need to also decide how to copy the data, because we don't have just primitive data type here now. It's node, which is something which is user-defined data type. So please think about it and post your answers in the chat. I'll wait here for a few seconds. Okay, let me go back to the chat if there are no. Okay, I guess there are no questions. Yeah, please feel free to try out. I'll wait here for a few seconds, and if there are no, there are no responses, or then we'll move forward with the next step. Yeah, but please try out so that you can at least get some idea of how to do it. Even if it's wrong, that's okay. Let me okay, explain SOA once more. So SOA is like we are placing all the attributes uh, of the entity together. So roll number are placed together in one array, then name is placed together in one array, then marks are placed together in one array. That is the structure of arrays. And it is called structure of array because we have a structure inside which we have the arrays, if you see here, like this. And the key advantage is whenever a thread, whenever we have threads within the what which are accessing the same attribute, which is, let's say this first attribute was roll number, then since we have stored this thing in array, all the accesses will be contiguous and they will fall inside the same block of 32 bytes, and the memory accesses will be completely coalesced, and we'll be able to see some advantage because of this if you use this on GPU rather than this, because this is trident and this is completely coalesced. I hope that's clear, Mridmoy. Okay, okay, then I think as we are running out of time, I think I should move further. Okay, so assuming that you have at least tried this, let us go to the next slide to understand how this thing works. Like, uh, let us say we have these two ways of declaring the data structures. How to access them on GPU? Let us see. First of all, how to mem copy them and then access. Let us see this. So let us say that you want to access array of structure on GPU. Then how will you be able to access it? So for that, first of all, you need to declare this struct as we did previously here also, like this. We need to declare this struct, and then we need to declare this pointer all nodes AoS, which is pointing to the this is just a pointer which is pointing to the array which are having elements of type node AoS. Okay, so yeah, that's on CPU. So we have this pointer pointing to the array of size n, which is on CPU, but we need to declare the array of this type again on GPU. So to do this, we'll do CUDA malloc. We'll use CUDA malloc, and to declare, to store, to allocate the memory for this type of element, we'll do n into size of node AoS. If you people know, like for allocating the memory for structures, we do something like this. CUDA malloc. And into size of that whatever that structure is, we'll specify it here. So we'll need to allocate the memory like this. Obviously there will be a second parameter which I'm missing here, but we'll need to allocate the memory, and then CUDA memcopy this CPU array into that GPU array. Once that is done, and we have hold of the pointer to the GPU memory location which is being allocated, we'll pass that pointer, that address using pointer, and it will be holded here using this pointer, and then inside we will just compute the ID as usual we do, and then using that ID we'll access the each and every elements. I mean each and every attributes of this this array. Please note that this all nodes AOS is now on GPU. I mean it's pointing to some GPU memory location because we did CUDA malloc and CUDA mem copy. And yeah, so this is the way in which we can access AOS on GPU. And if you see, this is strided access, right? Because a thread having ID 0 is accessing the attribute A, B, C. And if you recall, it's something like this. Let us say this was attribute A and this was attribute B, and it's strided access because same thread is accessing ARR of, I mean, the A of ID of A and A of ID of B. So you can correlate this with this thing. So this is strided access pattern. This will definitely degrade the coalescing. I mean, we won't be able to achieve full coalescing if we use EOS. And to make matter worse, if there are more attributes, here just there are 3 attributes. So the stride size will be of 3. But if there are more attributes, let's say 10, then stride size will be 10, and that will significantly degrade the amount of coalescing. So instead of doing this, what we can do is this. We declare this structure in different way, which is node AOS, and each attribute here is the pointer to the array. So here array is this, if you remember this array, but now we are just declaring pointers. This pointer will point to the appropriate array on the CPU. Once this array are pointed to the appropriate arrays on the CPU, we'll need to CUDA malloc the memory for each of these 3. We'll allocate the memory for each of these 3, and then we'll be doing CUDA mem copy for A, B, C respectively, and then that pointers to those 3 memories which are storing at the starting address of those arrays to the GPU kernel here, and then we'll be computing the ID, and then we'll be doing A of ID equals to ID and all these things. And one crucial thing to observe here is all the WART threads, when they execute A of ID equals to ID, this is completely coalesced, because for the 0 thread, A of 0 equals to 0 will be done. Second thread, A of 1 equals to 1 will be done, and so on. So you can correlate this with this one. A of 0 equals to 0, this, A of 1 equals to 1, A of 2 equals to 2, and so on. So this is very much similar with this one. So yeah, so this is the example of completely coalesced memory access. So SOA will give you complete coalescing, the maximum amount of coalescing that we can achieve for the warp threads, and this will give strided access, so partial coalescing, or even in worst case it might give completely uncoalesced if there are very large number of attributes. So this is one point to observe. And if you time this code for the GPU thread, I mean for this GPU kernels, if you time this 2 kernels using, I mean if you are declaring this structures and then you are launching the kernel and this is your kernel for both the cases, then you will see that EOS performs, I mean EOS takes 62 units of time and SOA will take just 22 units of time, and this performance benefit is coming all because of memory coalescing, if you see. So it's just almost 3 times benefit, I mean 3 times performance improvement that you can just by coalescing. So this is a sort of motivation why we should use SOA instead of EOS when it comes to GPU. For CPU, EOS is better, but for GPU, SOA is better. I hope that everything is clear up to this point. If there are any questions, I'll quickly take them up.
Sir, in this for node SOA, that picture, sir.
Yeah, please.
Yeah,
Yeah.
that node SOA, we have like pointers like A, B, and C, right? So for those pointers, we will be having to do CUDA malloc.
First of all, you will be doing malloc on CPU. I mean, you need to allocate memory on CPU. These are just pointers, right? So you will be allocating memory on CPU and making those memory point to that memory location on CPU. Once CPU allocation is done, initialization is done, everything is done, you will be then allocating memory on GPU using CUDA malloc. I hope that's clear. And then once once you have done allocation using CUDA-malloc and you have stored the starting address in some pointer, you will be passing those 3 pointers which are storing, which are corresponding to these 3 CPU locations to the GPU. Okay, if that's unclear, then let me go to the chat. So, okay, so let's say A was star. Please take care of this data type. This is something in star A. Just not typing the precise thing, but please understand this. That is n into size of int. So first you need to do this to allocate the memory on CPU. Once that is done, and you have, let's say you have allocated and initialized the memory, right? Now you need to allocate the memory on GPU also. So for that you need to declare GPU array, and again the same thing that I have written here, but this time it will be CUDA-malloc, right? Yeah, please assume that I have passed arguments properly. And then once this GA is ready and you have mem copied CUDA mem copy actually. CUDA mem copy GA2. So entire A array is copied to GA. Once this is done, so you have this now entire array on GPU, which is GA. You will be passing this pointer, which is pointing to GPU memory, to here. You'll be passing it here, and yeah, then this pointer, it will be pointing to the appropriate GPU memory location, and then you can access the way you want. I hope that's clear. Hello. If there are any questions, probably we have already reached the time limit. So if there are any questions, I'll wait here. But this is a small homework that you people should try. Probably I'll put this homework in slides and put slides on that sheet, and people can try this homework in your own time. So yeah, I'll stop here. We'll not move with the shared memory part for today because it's already time, and I don't want to push this further because it will take at least some more 10 minutes to start with a new topic, which is shared memory. So I want to stop here. But just in case any questions you people have, I'll wait. I'll be there here for a few minutes more, just to clarify the questions, and then probably we'll disperse.
Sir, could you explain how the array of structures like improves locality, sir, in CPU, sir?
Okay. Okay, so let us go back to this. Okay, so array of structure is something like this, trident memory access, because whenever you are declaring this type of data structure, this type of structure, ABC, it is stored contiguously. So let us come back here. So let us assume that you are declaring, for the simplicity, let us assume that there is no C here. There is no third attribute. There are just two attributes, int A and double B. So the way this is stored in the CPU, when you allocate the array of this type node, which is having two attributes, it's like this. So so this is the array. It looks something like this, and here this is the first element. Please consider these two blocks as the first element of the array. These two blocks as the second element of the array. So this first element will have two parts. One is A, one will be used for storing A, and another will be used for storing B. So that is one element. Then there is second element, third, and so on. So whenever you are doing access like this, this all nodes of 0 dot A, what will happen is this entire thing will be brought into the cache. This all nodes of A as well as all nodes of B. And next, when you try to access all nodes of B, due to locality, because it's already brought in the cache because of that special locality, if you remember from our previous lecture, the access of this thing will be very quick. So that is the advantage of locality with respect to AoS data structures on CPU. I hope that's clear. And if there are still any questions, I mean, there is something unclear still, then you can ask.
Sir, but even on the CPU side, if it is made like coalescing, it will be still better, no, sir?
No, but on CPU there is no coalescing because there is no SIMD execution pattern on CPU. CPU everything is asynchronous. No threads are executing in SIMD fashion. So memory coalescing concept is not there on CPU. I hope that.
So on CPU, we won't have like warp blocks or anything like that as well.
No. On CPU there is no concept of warp or anything. Warp is typically for GPU only. So in CPU, okay, so let us come to CPU if you are asking this question. Then in CPU, if you are launching, I mean, let's say on CPU you are doing some computation with 32 threads, then all these 32 threads will be asynchronous. Asynchronous. There will be no SIMD right thing, right? So it might happen that one thread is executing instruction I1 and another thread is executing instruction some I5 or anything. So memory coalescing is not done on CPU. Yeah. That's what I'll see. In fact, it's okay. I'll stop. I mean, it's not done on the CPU. It's completely related to the GPU, and that is why we are able to get improvement by using SoA instead of AoS on GPU. I hope that's clear. If there are any further questions, then please feel free to ask. Only 2 more minutes I'll be here.